Part 4. The sine laws on the straight counting line continued. The fourth and final sine law is the dual of them all. We want to show that -2 times -3 is equal to +6 on the straight counting line. In other words, to show that a negative times a negative is a positive. And the problem there, of course, is how to see that -2 lots of -3 come to a positive answer. Once again, we envision the straight counting line as a portion of this indefinitely great circle. And this is obviously not drawn to scale. We've got -2 here, as before, just 2 steps back from 0. As with the other sine laws, we start from 0 and we count around to this point -2, some positive value, and we don't know what it is. As before, it could be a trillion. And so we're being asked, for instance, what is a trillion lots of -3? And we'll get rid of that answer we had there, because just as we don't know how big this really is, 1 trillion, 10 trillion, whatever, we don't know what that comes to yet. Once again, just for the sake of argument, let's say that that value in there was 1 trillion. Then this sum is asking 1 trillion lots of -3. And let's just add on 2 more. So that's a trillion 1, a trillion and 2, or a full circle's worth of -3s. So there it is. There's the 2 lots of -3 that we added on, those 2. And that gives us the full circle's worth of -3. And fortunately, we know what that answer down there comes to. It's 0. And to see why, we can see that -3, there it is on that indefinitely great circle, has also got a positive value. We don't know what it is, but it does have such a value. And we've shown that once around times any number always comes to 0, and that includes any number found on this indefinitely great circle. Now for the fun part. To get to this line, and the answer of 0, we added an extra 2 lots of -3. There they are, to make it once round, lots of -3. So to get back to our original line, we have to take away 2 lots of -3. Here's one lot of -3, seen as being taken backwards from 0. And because we're treating the straight counting line as an indefinitely great circle, as shown here, we can also get to that value in the positive direction, seen in the green here, starting at 0 and moving in the positive direction clockwise around to it. Now we can't say how big that green value is, but we do know that it's at the point -3. What we needed to do was we needed to take this green value of -3, whatever it is, we had to take it away from the value we arrived at in this equation, the 0, so we had to take it away from 0. So to do that, we just start at 0 and we have to go in the opposite direction, we turn it round and we take it away, this way. And that brings us, of course, to the point 3, because this length in here, the pink length, we know it's of length 3. Now, in order to get from this equation back to this first equation, which is what we're really trying to get to, we had to take away 2 lots of -3, the 2 that we'd added on before. So we need to take away 2 lots of -3, and there you go, we've taken away 1 lot, and we just need to take away another lot here. So starting from this point, we take away another lot of that green, and there it is. Starting from there, we go around, and that brings us to this point here. Now, of course, this pink area in here is also of length 3, and so we've got 3 and 3, so we've actually arrived at the value 6, which is, of course, the same as +6, and so we've got that -2 times -3, -2 times -3 is equal to +6 on the straight counting line when it is envisioned as an indefinitely great circle. We'll end with a few concluding remarks. Firstly, these results are only possible because we're treating the straight counting line as a small portion of a much larger circle. And that means that negative numbers such as -3 here can be seen as having positive values which we can then manipulate to get our results. For instance, we can turn this -3 around and take -3 away, and we can show that very simply in the diagram just by reversing the picture. Secondly, this means, however, that we have contradictory conceptions of the counting line. One is as a straight line, the other as a circle. Of course, the straight line is the close-up view, which allows us to see the numbers but doesn't let us get to see the full circle. The circular view is the far away view. It lets us see the whole thing, but we can't see any of the individual numbers. And in fact, this brings mathematics up to date with modern physical science, which has the wave-particle duality, where a subatomic particle is seen as a point particle, and alternatively and simultaneously it is understood to be a wave spread across space and time. And these two opposed images appear to be what underlies physical reality, and so the mathematics now gives the child a chance to appreciate how this can come about. Finally, are we looking at demonstration here or at proof? All of the examples we've been using have been strictly numerical. Now that's because the children that we're preparing this for have not yet attained to the stage of algebra. In fact, an understanding of the sign laws is a necessary precursor for algebra. And so to that degree we seem to be looking at something that looks a bit like demonstration. However, when we look at the nature of the counting line that we now have, we can see that we've lifted off the written page and into the realm of the human imagination or the human understanding. And to that degree we seem to be dealing with something that's more like proof. So I'll leave that for you to decide for yourselves. But notice that where we've been referring to an indefinitely great circle, we're really meaning a circle of indefinite size, and that means that it could be any size whatsoever. We're really looking at a generalization of the circle, in much the same way that algebra generalizes numbers with their x's and y's. The x can stand for any number, and the circle of indefinite size can really stand for any circle. And so you can see that we're looking at something here which is approaching algebra. It's doing to the counting line what algebra does to the actual numerical values, and fits in as a perfect transition point between ordinary arithmetic on the counting line and algebra. Indeed, the next step would be to turn around and take what we've looked at here and use algebra to produce formal proofs. And that concludes our comments on the sign laws and the straight counting line.